So the next topic that we are going to discuss is about the various components present in the microwave. So basically, we are going to look at the uh, various types of cavities which can carry the signal from a source to the load. Okay, so the first category that we are going to discuss here is called as the waveguide. Waveguide junctions. Right. So it actually becomes very much necessary that we have certain waveguide, okay, and we give certain amount of energy, right, as input, okay. But most of the times in microwave circuits, it becomes necessary that you share the input energy, right, among multiple devices. Okay, so I may have to connect few devices as load. Okay, so this is the input, and we may want that this input energy gets split in certain fashions so that you can receive or you can deliver, right, them in three or more devices as output. Okay, so that could be output one. So here I may have a requirement of getting output two and an output three, like this. Okay, so it becomes necessary that you split the energy or a part of the microwave energy in particular direction, right? So this is our requirement. Splitting up of or splitting the microwave energy splitting the microwave energy in certain directions, right? Because we need to split. This is the first thing. So this can be achieved by the waveguides or in general, the junctions of waveguides. Okay, so this is something like we have certain combined form of coupler units that direct the energies as required. All right, so to direct the energy as required, in order to direct the energy as required, we are going to use what is called as a coupler units. Okay, certain coupler units are used. All right. So they are going, there will be a junction, and from the junction, you can take out two or more signals as per the requirement. Okay. Now, the junction is normally it's going to have four different ports, right? So if you remember, maybe in the electric circuits, right, we might have already studied what is called as a two-port network, correct? This is a pretty similar concept, right? But we use four ports here, at least four ports will be, right? So this is the concept. So whatever we are going to discuss here will be an extension that is compared to the two-port networks we already have studied, right? So a junction is required to interconnect to interconnect the coupler units. So normally, what is the size? four units can be connected, right? This is the general application. One input, three outputs, so that you will have four coupler units can be clubbed together in a junction. Okay, right. So now let us see the general architecture of a waveguide junction. So in general, the waveguide junction looks something. Okay, so we have various. Okay, we let's assume that we have one source connected to this. So this is a source number one. All right. All the other components that you connect are the loads. All right. One source, many loads. So in this case, again, as an example, we know that we are considering a junction which can connect four devices. Out of the four devices, we have, let's see. Okay, so we have three different units that will be considered as the load. Okay, so this is an approximate say diagram, and let's try to connect. So this is connected to the device like this, all right? And let's also connect this. It's connected to every device, all right? So that's a junction at the center, and to the junction we connect several devices like this. Okay, so this is how it's going to look like. So at the center we have the the junction. So we'll write microwave junction, right? So from the left side, let's assume that that is a source, all right? So this is a microwave source. Others will be the load. So microwave load, microwave load, microwave load. So if you look at the the port number, maybe this is port number one. We can give the numbers in say clockwise fashion, right? So port number two, this is the third port, right, to which we actually have connected that particular device, and this is port number four. Okay, now what are the possible directions in which we observe the energy flow, right? So we can, all the ports are normally bidirectional. That means I can see the energy flowing in this direction. At the same time, the energy can also flow in the opposite direction, right? So when we design, we have the complete options like this. Okay, so energy can flow to the from the junction to the load or load to this. It's possible in both the directions. So let's mark the directions like this. So generally, we can think that this microwave junction is not is pretty much similar to the on a road when you when say four roads meet at a point, right? You can see that, right? It's pretty much similar, right? So vehicles can enter the junction and vehicles can leave from the junction. That's all. Okay, pretty much straightforward. So let's go ahead. Now, how do you measure the various parameters of a junction, right? This is pretty much similar, right? Recall the two port network, right? If you remember the two-port network, the input and the output parameters of any two-port network can be measured by using, right? Do you remember what are the various parameters you might have used in a two-port network to measure the parameter? In a sense, you can measure, right, the input current, output current, input voltage, output voltage, etc. with respect to a given two-port network. But whenever the exact values of the voltages or currents are unknown, you used the parameters, which are the ratios, right? For example, right, if you remember, one of the parameters used is called as a Z parameter. Then you also have Y parameter, right? The hybrid H parameters and the ABCD parameters. Do you remember? Okay, so let me just write the parameters used to characterize microwave junctions are. So if you remember, it's pretty much similar to the two-port network, but as of now, it's not going to be a two-port network because we have four ports here. So in the four different ports of a network, right, we try to measure what is called as the S parameters. Okay, S stands for the scattering. All right, so let's try to explore this further. Now, in this case, in case of our junction which was considered in the previous diagram, right, we can observe that out of the four ports, one port is the input. All right, so we can apply the inputs to any of the port, right? When what are the total combinations, right? Something like I give input to, I can provide the input to any of the uh, four ports. Normal connection is like what we had seen earlier. In that normal way of doing the connection, right, I give input from one side, okay, I take outputs from the other three sides. But this can be changed to any port, right? I can give the input from any of the four ports. When you give a input from one of the port, you can take the output from other ports, correct? So, right, in a microwave junction, say with four ports, right? What we can do, right? The input can be applied to any port, and the other three ports are the output ports. Now you tell me how many such combinations are possible, right? So this can be, when I give input to one of the port, I can definitely look at the concept. I can actually do the analysis in such a way that I can calculate what is the amount of energy that comes at each of the port, right? I give energy to first port, some amount of energy goes to the second port, some amount goes to the third, some amount of the energy goes to the fourth, and some will reflect back. So when I give input to one port, I have all these things happen. So you see, if I try to write that particular measurement as a row of a matrix, I can call it as I give certain amount of energy, something comes back to the same port, something goes to the second, something to the third, something to the fourth. So when I write one row, I have four different options. Okay, but you see, this can be repeated four different ways, right? Because I can give input to the second one, right? You write one more row. When you give the input to the third one, you write the third row. of a matrix, and when you write the fourth row, you will write another row of the matrix. So you see, totally we have four such rows. Each row has four parameters, correct? So what in general we call that? We call that as a scattering matrix. Okay, so let me write another sentence over here, right? So considering the input, right, given to all four uh, combinations, let me make a change, given in all four combinations, this implies you have 16 possible values. All right, 16 possible measurements. Okay, so it's very clear that I have four options, so totally 16 options. That means I can try to write a square matrix, right, containing all the possible combinations of the power relationships between various inputs and the output ports of that junction, right? Okay, so this implies we can write we can write all such, say, combinations, all such combinations of the power relationships, all such power relationships between what, between the input and output ports of the microwave junction, right? We can write that in which format? In a square matrix. So okay, in a square matrix, right? So such a matrix is what is called as a scattering matrix, square matrix. So it's called scattering matrix. All right. So inside the matrix, we have the elements, and those elements are referred to as the scattering or S parameters, right? So the elements. So I just write here, this is S matrix. All right, the elements of a S matrix are called as, they're going to be called as the S parameter. All right, okay. Now let's try to look at this in view of a circuit. If at all I'm trying to write a circuit, right? Let us see how we can try to represent, right? Represent these parameters. How do we derive that? That's our first objective. So this is a general concept, right? Later on, we'll modify this general concept to the specific cavities. All right. So there are various types of junctions, right? For example, you may have what is called as a H plane T junction. Then you have a E plane T junction, depending upon whether you are dealing with the magnetic field, electric field, etc. Then also you have a hybrid junction which contains both magnetic and electric fields. All right. Then there is a magic T junction, a rat race junction, etc. Where various types of junctions are available, right? Okay, out of which we'll look at the most common ones at a later stage, wherein we are going to apply the concept that we are going to study now in the most general way. Okay, so we'll study the general concepts now. Later on, we'll modify according to the properties of each of the junctions. All right. Okay, so let us consider a case where we'll try to write it in the following junction. Okay, so let's try to look at the circuit view of that junction. Consider the circuit to be consider the junction to be a circuit. Okay, so let us say this is the port number one, where we are trying to provide certain input. Okay, certain input is provided to this. So let us assume that this particular port extends up to a point. Maybe this is the point where we can say that, okay, the port exists. This is the input port which existed here. And at this particular point, right, we have a junction coming into picture. Okay, let me write like this. So this is the point where we have uh, many branches of the circuit gets divided into many branches. All right. So both of them are the nodes of my circuit. Okay. Now the first, let's write only few of them. Say like this. This is the first branch. Let us assume. Okay. So that's one branch, but I will copy that into many things. Okay. So okay, and let me assume we have nth such branch maybe over here. Okay, now let's make the connections. So this gets connected to this point, and this particular point gets connected to this. Okay, at the same time, you also have the connection between this and this point, and the lower one getting connected to this. You see, this is considered as the second, right? From the junction, you have several branches. All right, so it is compared with a particular node in the circuit. From the node, you have many branches going on. So since we already know the concepts of the nodes, right? We are trying to make things clear, makes things easier by comparing. Sorry, by comparing that with the comparing a junction with a node in a circuit. Okay, right. So let us assume that we have several such branches going on. Now let us not assume that this is only four, right? There are only four branches. We assume that there are many branches. Okay. So let me try to write something over here. Let us say the energy that is supplied by this source, whatever it flows here, let me assume that as the, okay, let me write another notation here. There is a ith, some ith line. This is some ith line. Okay, so I'll write the input energy as AI. Okay, and whatever that gets reflected back on the that particular path, let's call that as BI. Okay, very similar to that. Let's do let's call some, let me give some names so that we can trace it. So let's say this particular line is the first line. Okay, this is This is the first line. So here, what I'm writing is this is the second line, and so on. Let me say we have n lines. So this is the nth line possible. Now you see what are the various types of energy flows, right? From the branch, from the node, we have energy that is getting splitted up. So this energy I'm going to call it as A1, and whatever that gets reflected is B1. Okay, so the energy that flows on this line, I'll call it as A2. Energy gets reflected is B2, right? Very similarly, the energy that flows here is AN, and energy that gets reflected is BN. Okay, right. Now we can actually have many. So this is something like, right. You try to recall the concepts we studied in the transmission line. So in order to get this kind of mismatch, what is the value of what is the condition on ZL? So if I say there is ZL, ZL1, ZL2, etc., right? What is the condition on ZL, right? So that there is a reflection. If you want to have a reflection on a particular line, right, particular transmission line, what is the condition? Under what condition you will have reflections on your line? Is my question. Any idea? Okay, no problem. So the fundamental condition is that if the load does not match with the characteristic impedance of the line, then there is a reflection. Okay, so that means ZL is not equal to the Z naught of that particular line. So that's what is the condition here. So because of which you have the reflections. Fine. Now, uh, right? So we have the various components like this. Now, if at all ZL equal to Z naught, then you see there is no reflection, correct? So let me write one point here. If the ZL becomes equal to Z naught on any line, right? This implies no reflection. So this could be one of the possible cases, right? We can also actually split the whole concept into two or three parts, where in the first part we'll say that, okay, consider few of the lines are terminated with the proper Z naught value. Okay, ZL equal to Z naught is matched. Maybe, so only, let's say that only the first line, I'll show the, this thing. I'll show you the diagram once again so that we can consider that to be one of the cases. So you can think that only the first ZL is not matched, right? So let's say this is the case, and in all other cases, this is not the condition. In the sense, ZL equal to Z naught, let's say so. Okay. In such case, what happens, right? I have to make sure that when I write such a condition, right, I will be writing the B2 equal to 0, because in along B2, right, this matched means B2 becomes equal to 0. This actually matched ZL equal to Z naught means BN is equal to 0. I can write it as a, right, I can write that as one of the condition, and only B1 is related to A1, other terms are not there. Correct? So ith line gives an input, one of the line only reflects, other lines are not reflecting. This is one possible case. Correct? Right? So maybe, right? Maybe I can try to write that as well, right? But anyway, we'll come to that at a later stage, right? This is the first point. If ZL equal to Z naught on any line, no reflection on that line. That means the B becomes equal to 0, right? So this implies the Bn whatever, right, becomes equal to 0 in that case, right? Otherwise, Bn will not be equal to 0. But as of now, in the diagram, we are not considering Bn to be 0. I just wrote the other option, that's all. All right. Next, let all the lines they are terminated with an impedance. Terminated with an impedance, right? ZL not equal to Z0. Okay. In such case, we can see that there will be reflections into the junction from every line. Okay. So every line sends reflection to the junction. Is it okay? So you see that there is a total contribution to the outward traveling wave in the ith line. What is that? Along the ith line, you can see which is the ith line. That is the input line. Whatever that goes over there, bi is nothing but, how do you get this bi? Bi is nothing but, it's simply the sum of each of them. Correct? Right. So let me try to write. So this implies, I can try to write it this way. This implies the total contribution to the outward uh, wave, that is bi, outward wave bi, in the ith line. So how do you write? This is b1, sorry, bi should be equal to the b1 plus b2 plus b3, right? I'll write like that. I can try to write, this is the bn. Now you see, right, we try to represent a parameter, that is Si1, which says what is B1. Okay, B1 can be written in the format of S parameters, right? So try to recall. I can try to write a notation here, right? So, okay, I'll write a, since we are discussing for the first time, I'll write the complete equation as well. So call this is 1, okay, but the any bi can be written as any general bi can be written as si1, okay, si1 a1. So it's like si1 a1. So this is what I'm trying to write it as the general form. All right. So I is the source connected to the ith line. 1 is the reflection from the first line. That's what I'm trying to write. Okay. So this is the general representation. Okay. Let me try to write it in this way. Okay. Let me try to write a B1. B1 is equal to Si1 into A1. Let me try to write it that way. That makes more sense. Okay. So that means I can try to write, this implies the Bi is equal to, what is B1? Si1 A1. Okay. That means the amount of reflection on the first line is Si1. Okay. And 1 says that it is the reflection from the first line, that is a suffix. All right. B1, A1, Si1, there is 1 written over there. It indicates that it is a reflection actually. We are talking about the incident wave or the reflected wave on the first line. That's why it is S like that. Okay. Si1. The next part is that I'm talking about what is I. I means it is the source connected, right? From where you are getting the energy to this particular line, that line is denoted by I. Okay, so now you see Bi is equal to Si1 A1, that is nothing but the amount of reflected energy that is reflected by the load connected to the first line. Similarly, plus B2 is required. So this is Si2 into A2. A2 is the incident energy, Si2 is the scattering, how much reflected back. All right. So like that I can extend. So this is plus, I'll write one more, say Si3 into A3 plus, go to the last component. All right. So that is plus Sin AN. There are n different ports in the given network. Okay, right? So let me call this as equation number 2. Okay, let's proceed. Now, you can, now this is written as this is a very general form of equation. Okay, now we'll try to extend this. Now I can actually provide the input from any of the line, correct? Right? So you see, I wrote an equation for Bi only. Bi indicating that I assume that out of n different ports present in the system, right, I'm giving a input on ith source. For example, if you have 4 different ports in a junction, you can give input to the first one, second one, third or fourth one, right? But when you give input at the first one, 2, 3, 4 are the outputs. Now in this case also, what we have considered is that there are n different branches. Okay, there is a junction in the circuit, and from the junction I have n different branches. Out of those n branches, input is given to one of them. Okay, so you took output from the remaining, right, n minus 1 branches. Okay, so now you see this, I will try to expand this equation. I'll try to expand, so that's how it should be. So now so I can vary from 1 to n, correct? So that implies, let's try to because 1 to n, this is okay. I'll give you an explanation here. 1 to n as input can be given at any at at any of the n lines. So that means if at all you give it 1, so this is the condition. You see, S, it is I1, so S11 A1 plus this is S12. Replace the I as 1 now. S12 A2 plus this is S, all right, plus this is S13 A3 dot dot dot. What will be the last term? This is not here, sorry. It's S1. I can write S1N AN. There are n ports. So let's write few more equations. Maybe B2 also I'll write completely. Okay, this is S21 A1 plus S22 A2 S23 A3 dot dot dot. This is S2N AN. So let's go to the last option, because I'm very sure that there are n different ports possible, correct? So because of n different ports, I can get how many equations? N equations. So Bn can be written in the following way. Okay, that is Sn1 A1 plus Sn2 A2 plus Sn3 A3 dot 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 plus SNN AM. This is for n different ports being present in that particular junction. Okay. Now let us try to write the same thing in a matrix format, because everything becomes simple if we look in the matrix format. So, right. So converting to matrix notations, we actually get B is equal to S into, right, A matrix A, right, where let's try to write what is B. B means your the left hand side, B1, B2, B3 dot 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 up to Bn. So this becomes a column vector or a column matrix. Okay. Similarly, I can also write there is a S present in the given system, right? So let's try to write that S equal to S11, S12, dot 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 up to S1n, right? Second line S21, S22, dot 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 up to S2n, Like that, I can write n different rows below this totally to get Sn1, Sn2, and Snn. Now you see n rows, n columns, so that's why this is a column matrix. Okay, and also we write A. So A is equal to, right, the various inputs on the lines A1, A2, dot 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 up to An. So you see this is also a column matrix. So the B matrix is said to be the reflected waves or the outputs. All right, so let me write below this. So this actually represents the reflected, or you can even call as output components on different lines if you are considering them to be considering it as a circuit. And if at all you are considering them to be the junctions, right, it's the output corresponding to each of the junction, right? Then we have what is S? This is the scattering matrix. Correct. Again, that is specific and corresponding to a given junction. I have a specific S matrix. It's not a general one. It's not going to be the common one for any junction you consider. All right. Then this is actually the incident or the input. Okay. Components are written along this. All right. Now, now there are some specific features that we are going to observe here. Whenever I look at this particular S matrix, I may find out there is a Sij written. Okay, S12, S14, S23, S24, S21, etc. Okay, so Sij is nothing but it's a we are going to call them as the scattering coefficient. So they are resulting due to a specific reason. Okay, so uh, resulting due to input at ith port and the output at the jth port. So I give input at this port, I take output at this port. So that is what that relationship is Sij. So this is ith input, jth output. Okay, so you have a junction like this, maybe. All right. So you see ith, your ith port. So this is, say, port I. This is port J. So from the input is provided to the ith port, output is taken at jth port. If that relationship is what you want to measure, then we are going to use it as Sij parameter. You can see in the matrix, right? S12, S13, S14, S1n, S21, S23, etc. So the numbers you write are different, not same, not S11, not S22, not S23. So that's another parameter like SII. Okay, same number. So previous one is Sij. Now we are talking about SII. Okay, so this denotes the power reflected back from the junction to the ith port when I can write, say, when the input was given to the same port. Okay, that's why it is SII, like S11, S22, S33, etc. So you give input to the port number 3, and when you give input to that port, how much power gets back, right, to the same port from the junction is that. So when the input is given to the same port, so understand the difference, right? The diagonal element, the diagonal elements of the matrix, uh, S matrix, they correspond to the reflection coefficient. How much power you give, how much gets reflected back. That's what is that term. And there is another concept, that is Sij, where I and J are not same. In such case, you see that the power that is available in a particular jth port when the input is given at the ith port. All right. So that's the explanation for the S matrix representation. So this particular S matrix has certain characteristics. So we call them as the properties. Properties of S matrix. Okay, so we'll write the properties. All right. The first thing is that it is, just now we have observed that there are n ports. Any port you can give input, any port you can take output. So it will be a n into n matrix. Okay, it is always a square matrix, right? So that is of the size n cross n. And there is one more property associated with that. I'll just write like this. This means the S matrix is always symmetric. What do you mean by sorry, my spelling mistake. Correct that. Okay, this is symmetric. So what do you mean by that? If I have a value Sij present in that, it's also equal to Sji. Okay, S12 and S21 are equal, right? S23, S32 are also equal, and so. So we always represent, right? We'll also always see that it's a symmetry. So that, what is the physical meaning of that? I give energy to the second port. If I give energy to the second port, certain amount of the energy comes to the third port. You reverse it. You give the same amount of energy in the third port, right? Whatever was the ratio, it uses the same ratio and you get the same amount in the second port. So S12 is equal to S21 means that. Yes. Perfect. Right. So now I'll bring the what you call as the identity into picture. So fundamentally, from the matrix chapter of mathematics or linear algebra, we know what is called as a unitary matrix. Right. So this particular matrix is unitary. So what do you mean by unitary? It's pretty simple, right? So there is one. It will satisfy the following condition: S matrix into the S conjugate matrix equal to the identity matrix. All right. So this is the identity matrix. All right. So when I multiply S with its conjugate matrix. So let me write this. This is conjugate S matrix. Right. So whichever matrix satisfies this particular condition, the condition is that take a matrix and multiply this matrix with its conjugate matrix. So what do you mean by conjugate? If you have a complex number as an element of that matrix, take its conjugate and write that. That's all. All right. Okay. Now let's say that's our third property, right? Then we'll go for a fourth property of this. So sum of the products of each term of any row, it means any row means it is also applicable to column, multiplied by the complex conjugate corresponding to the terms of any row or column equal to 0. I'll just write the sentence and I'll also give the equation for that. Okay, so this is the property, next property. The sum of products of each term of any row, or I can also write or column. Okay, multiplied by multiplied by the complex conjugate of the corresponding terms of any other row. Okay, not the same row, other, any other row. Since you can consider column also, so I'll write or column. Or column is 0. So this is the meaning. Let me try to write a equation for that. All right. So that is, we, how many i's you can have? I varying from 1 to n. Sum of the product. So what I can write, this is si, say some other element into the conjugate of the other one. So since I used k there, it is sij conjugate. This is equal to 0. Right? So take a element and take any other elements conjugate, right, which is not present on the same row or same column. That if you do the summation of such products, it's always equal to 0. Right? So here the thing to note is that k and j cannot be same. If k and j are same, it is the same row, right? Okay. Or if you are considering column, it becomes the same column, right? So whenever the row you are considering and take the elements of the conjugate from the next row, any other rows, right? And to take a product and take the summation at the end, you get 0 as the final value. Right? So what we do, we use all these properties to find out the S parameters of various junctions possible. Okay, so in the upcoming class, what we are going to discuss is that we'll start with the microwave junctions, right? Specific junctions. Now, till here, till today, today's topic, whatever we discussed, it includes the general topics. Okay, and we introduced the concept called as the S matrix. And also, in addition to the S matrix, we try to understand some of the fundamental properties. Okay, so in the upcoming class, we are going to look at, first we'll start with the H plane T junction, then E plane T junction, hybrid junction, magic T junction, and so on. All right, so those are the major four this thing, right? T junctions. Then we can also look at the other topics required if they are present in your particular syllabus.